important. So in 1950s, okay, the fluid dynamicist, the Taylor and the Newman, okay, so they have done a dimensional analysis on this. You can see the atomic bomb here. Okay, atomic bomb. It is in the shape of the mushroom. You can see it. It is in the shape of the mushroom, and they have done an experiment. So they have actually done the dimensional analysis on this atomic bomb without doing its experiment, and they found the formula that governs the relation between energy and they found the energy and its properties. Okay, so during atomic explosion, what you have is that you have the energy released by this bomb. Okay? That energy is a function of some parameters like its radius or its density. It can be the temperature, etc. Okay? So by only writing this, the shape of the function and working with dimensional analysis, okay, working only with dimensions. Working with dimensions, they have found half E is a function of the R rho T. For example, I say, but it cannot be true, but just an approximation that the R squared rho by T, for example. Okay, so they have found this relationship, okay, and without doing an experiment and without you cannot get closer to atomic bombs. Okay, it is impossible. With only working with the dimensions of the properties. Okay, that's all. Okay, so what they have achieved. They have achieved to save money. Okay, they saved money, and this is the first part for the importance of the dimensional analysis. The second importance of the dimensional analysis is that what you are doing is that you are not producing the expensive full-scale production, but you are working with the model. We say that you are trying to produce a car. This is the prototype car, real car. Prototype means is real. So what you are doing is that you are not producing the real car. You are producing. So you are preparing a model one. Okay, you are not producing this one, but you prepare a model one, smaller one. A small. This one, as you can see, it is small. Okay, with these small dimensions, you get the properties that you want. For example, you get. Let me give you some options like the friction force. Okay. Or you can get, the main important thing here is that friction force, or that you can assume the fuel consumption. Okay. So by working on the model one, and you can also find the forces acting on the model car, by working with the model car, you get the values on the real car. Okay. By finding the values, and you are trying to estimate. It's not true to say it estimate, you can say it to calculate. Okay. You calculate the properties on the real one. Okay. This is another importance of the dimensional analysis. But we have said it, the two important things is that, first is that the cost, you are decreasing the cost here because it is the model, it is the real one. Model is cheap, so therefore you have the cost issues that's been solved. And the second thing is that, so you are doing that for the real one, you need a large wind tunnel. For the real one, you need a large wind tunnel. For the model one, you need a small wind tunnel to get the properties on it. Again, the second option also comes to the cost, but the main thing here is that you have the cost. But if you consider the atomic bomb here, it is not the cost that is important, it is the easiness of the result, because this one is very dangerous, okay, and you get the value without even doing the experiment, okay, by the dimensional analysis. This one is the topic, dimensional analysis. I will talk about later. And then the number of variables decreases. Okay, you will see in next slides how it decreases. The number of variables decreases, and then so for example so say that you are looking for, so I will talk about this one in next slides. Okay, let's keep in this mind. And also, so it increases our insight about the key parameters. Okay, so now this one will also in the next slide. So what I mean here is that how do we increase the insight about the relationships between the key parameters? Okay, we will see this and that one in the next slide. Okay, so as I said it, this one is the prototype one or the real one, but you're not doing the experiment on the real one. You do the experiment on the model one, and you get the values for the real one. Okay, from the model, you are getting the values for the real one. Okay. Let's give you one simple example. Okay, so our example will be concentrated on the car because it is more general example, and also it is easy to imagine. So the force that is acting on the car, it depends on the length of the car, velocity and density of the air, velocity of the car, and the viscosity of the air. And the force here, I mean that the force by air. Okay. The aerodynamic force, you can say. Aerodynamic force that is acting on the car, it depends on the 4 parameters here, the length, the velocity, and the rho and the mu. Okay. And you cannot find the relationship between them by mathematical analysis because it is very complex flow that happens over the body. Okay, then find the relationship between the force as well as these variables here. We need to do an experiment. Okay, so the experiment is that, so firstly, I plot the force versus velocity, okay, the force versus velocity, and I keep rho, L, and mu as constant. This is the first experiment. In the next experiment, I keep the force versus rho by keeping velocity, and then this one is velocity, and the length and the mu as constant. Mu is viscosity. And the next experiment is that I do the force versus the length, okay, and I keep the rho, v, and the mu constant. This is the third experiment. And another experiment is that I do the force versus the eta, mu, and keep rho, L, v, and rho, L, and the v constant. You can see that this is the one part of the experiments. But for this one, you need at least 10 values, okay? So the 10 different values of the rho, L, and the mu is constant, and also 10 different values of the velocity. Similarly here, 10 different values of the v, L, and the mu combinations, which should be constant, and therefore the values of the density. Okay, overall, what you will do is that you will do the 10 experiments for each L, and for each L, you will get the 10 values of velocity, 10 values of the density, and then 10 values of the viscosity, because you should keep them constant. So what I mean is that, so that F versus L, you are plotting it, and each time you keep the velocity and the density and the viscosity constant. Okay, but you take, for example, velocity 1, rho 1, mu 1, and then velocity 1, rho 2, mu 1, velocity 1, rho 3, mu 1. Okay. But you keep these values constant during the experiment, okay, and plot F versus L. And then you again plot F versus L, keeping velocity 1 and the rho 4 and the mu 1 again. You see, overall you need 10,000 experiments to find the relation between F and the length, velocity, rho, and the mu. Just to find the relationship between 4 variables and the force, you will need 10,000 experiments, which is time-consuming and expensive. Okay. But what is the simple approach? Simple approach is that doing experiment on these 4 variables, I can do experiment on 2 variables. One is that F by rho v squared by L squared. This is the first variable. And the second one is that rho v L by mu. Okay. These two variables here, the first one and the second one, gives the idea, gives what happens over the car with these 10,000 experiments. So how it gives, let's see that one. Okay, so I'm doing just one experiment here, which is F by rho v squared L squared. This is the first variable. Okay. My second variable will be this one. This is not a random process that I'm selecting my random variables here. This is not a random process, but we are doing the dimension analysis and to do the experiment. But you should believe that the plot here, the one plot here, conveys all of the information that is present in all of these plots. Okay? Instead of doing 10,000 experiments, by 10 experiments, you can get all of the information that is present here. Okay, with these two variables. What I have done is that I have decreased the number of variables, which was f, the rho, v, and the mu, and the l. So previously it was, let me write it, force, velocity, eta, the viscosity, and the length. It was 5 variables. Now it is only 2 variables. Okay. With the power of dimensional analysis, you can decrease the number of variables, but you get the same information. Nothing changed. You have the same information, and you have the better insight onto the variables. Okay. But here you see that I'm changing the velocity and the rho, but here you are only changing this value here, rho, v, l, mu combination. So you can only change velocity, or you can only change the density. Okay, but at the end you will get the same information from these experiments. Okay, this is another good thing about the dimensional analysis. It decreases the time to do the experiment, and it, as I said, the cost becomes less. And then the power of the dimensional analysis, I've said it is the first one we have said, that the time, and now another good thing about the cost. Okay. Why the cost? Because if you do the model one and there is a prototype, which is the real one, okay, you are doing experiments on the model one. But you don't know that whether these experiments will be also the values of this experiment, results of these experiments. You don't know that whether they will be valid also prototype one or not. You don't know it. Okay, you are not sure that whether the experiment results of this one will be the same as for the prototype one or will be the similar one. We don't know it. But with the power of dimensional analysis, you have the 2 variables. I've said it, this one and the second one. Okay, these 2 variables. With the power of the dimensional analysis, if these rho v l by mu combination, so rho v l by mu, this one is for model, and the rho v l by mu for the prototype. Okay. If this is the same, okay, if this ratio is the same, it means that the model is similar to prototype. Similar means that the values or the results of the experiment that you get from the model, you can apply with some coefficient, and not exactly the same one. For example, say that the friction force here by air is 10 newtons friction force on the car, and you are trying to find what is the friction force on the prototype car. Okay. To be able to apply the result of this one on the real one, you should first to be sure that the equation here is valid for the model as well as the prototype one. If it is valid, then the force here, 10 newtons, will be on the prototype car with some coefficient. For example, it will be 20 newtons, or it will be 30 newtons. We will find these coefficients in the next slides, but I'm trying to show the importance of the dimensional analysis. So this is another important thing about the dimensional analysis, is that it helps you firstly, it helps you the decrease of the variables from 5 to 2. And second is that it helps you to get the results from the model car by equating the variable for the model to the prototype one. If they are the same, and then these 2 are the similar, and then the force acting on the model one will be the proportional to the force acting on the prototype one. Good. This is another important stuff about the dimensional analysis. Now let's do a small review here on the dimensions and the units. So that dimension is a measure of the physical quantity. This is the definition of it. For example, the length and the mass, time, temperature, these are all dimensions. Okay. And they don't have any numerical value here, so dimensions do not have any numerical value. And the unit, it is a way, for example, Kelvin. If they say Kelvin is a unit, it is a way to assign a number to the dimension. Okay, for example, the Fahrenheit or the Celsius. And when we say dimension, we mean the length, we mean the mass, we mean the temperature. And when we say the unit, we are trying to assign a number to that dimension with some, for example, Kelvin, Fahrenheit, Celsius, etc. Meters can be. Okay, so there are 7 primary dimensions, you know it from physics, that is used, and the rest non-primary dimensions can be constructed by using them. These are also called the rest non-primary dimensions are called derived. Okay. They are derived from the primary ones. Okay, so that here you can see the length is dimension and the centimeter is unit. And the angle, revolution, and radian, they are not having any dimensions. They are dimensionless units. Okay, they have the units, but they don't have any dimension. Another thing about the dimensions is that you should have always the dimensional homogeneity. So you cannot add the apples and the oranges together. Let me give you one example. So x is s0 plus v0t plus half gt squared. Okay, it has a dimension of length because the s here is a dimension of the length. S0 here should be dimension with the length. V0t, it should be also the dimension of L, and this one should be also the dimension of L. Otherwise, you will not have the dimensional homogeneity. Okay? In each of the terms, you should have the same dimension. Or the Bernoulli's equation, you can see this one has a unit of the p by rho, but say that you don't know what is the unit of p by rho. Even you don't know what is unit of half v squared. You are trying to find these 2 units. You can find these two units from the third one, which is the GZ. Okay, the GZ is the mgz, if you remember it, potential energy, and without m, it will be that joules per kilogram. If it is joules per kilogram, by dimensional homogeneity, this one is also joules by kilogram. This one is also joules by kilogram. Okay, so therefore, and if you write in the dimensions of the primary units, length and the time to the power of -2. Okay. That is the power of the dimensional homogeneity. This one is for the units, so joules by kilogram, but you can convert this units joules by kilogram into dimension, and in that dimension it will have the length by time squared to the power of -2. But you can also get this dimension from the v squared here. Okay. So when we say dimensional homogeneity, the dimensions should be all of them the same, okay, the additive terms. Or change of a total energy of a system. That is the sum of internal energy, sum of potential energy, and the sum of kinetic energy. So all of them have the same unit and the same dimensions, which is the mass, the length to the power of 2, and time to the power of -2. That is the dimensional homogeneity. Okay, good. Now comes the similarity laws. There are the 3 similarity laws. What they are used for? They are used for the experiment. Okay. If you are doing experiment on the model car, you are trying to find the values for the prototype car, you should be sure that these are similar. Okay. And to be similar, if you remember, for example, from the triangles, the similar triangles, we had different rules between the angles. We had the rules for the sides. Okay. Similarly here, there should be the similarity between the prototype and the model car. The prototype is the real one. And the first similarity rule is that the geometric similarity. The ratios of the geometry of the prototype and the model one should be in some constant ratio. For example, if the model has a length of Lm, then prototype has a length of Lp. This Lp by Lm, okay, should have the same ratio for the tires or wheels of the car. If it has the wheel diameter of dp, and this one has the wheel diameter of dm, okay, which is the model, and the p here is that prototype, and these 2 ratios should be also with the same coefficient. You can take another ratio here, for example, the width, this one. And you can take the width of this one, width model, and the width prototype. Okay. This should be also width prototype divided by the width model. Okay. All of them should be the same coefficient. The first thing is that geometric similarity. Second is that the kinematic similarity. Kinematic similarity is that at any point over the car, the velocities should have the constant ratio. For example, for the real car, this is the flow trajectory. Okay. For the real car, the velocity at the front of it is VA, and for the model one, velocity here is V model A. Okay. But the ratio here should be same for the velocity of the fluid particle at point B, at location B, to the velocity of the fluid particle at point B for the model one. Okay. They should have the same velocity ratios at different locations. Even you can take, for example, the point here. Let's say that velocity C. Okay, here also. You are taking the velocity on the same locations. Okay, on the same locations on the same streamline. Okay. Therefore, that VC for the model or prototype should be equal to VC for the model. Okay. You should keep the velocity ratios the same. Okay. In other words, you have to have the similar flow pattern. You should have the similar flow pattern. Okay. For example, for the first car, if the fluid particles follow a profile something like this one, if the fluid particles go in that way, for this one, if the fluid particles go in opposite way, these are not similar. You see, the velocity profile for this one, velocity profile for this one, they are not similar. Therefore, we cannot talk about similarity for this case. This is the second condition for the similarity, velocity ratios. And the last condition for the similarity is that force ratios. Forces also should be with a constant amount of the coefficient. For the model car, if you have a force of, let's say that 5 newtons here, for the prototype car, if it is 10 newtons, so you see the ratio is 2. But if I take another force here, say that, you don't know that what ratio can be, for example, weight of the prototype and the weight of the, so weight cannot be a good ratio here because it doesn't play any role. But if, say that sigma, surface tension, okay, surface tension, it had a role here, okay. If it was important, then the sigma for the prototype and the sigma for the model should be also equal to 2. Any force that is considered to be important here, for example, that is, let's say that the lift force here, F lift, okay, the force that throws to lift the car. Similarly here, F lift, and F lift prototype divided by F lift model, it should be also the same coefficient. So the forces should be the same ratio, in the same ratio, okay. And if, for example, surface tension is very small in prototype, it should be also negligible in the model too. So anyway, we have the 3 rules for the similarity. First rule is that geometric similarity, the ratio of the lengths. Second one is the ratio of the velocities. And the third one is that ratio of the forces. These are the 3 basic laws of similitude. Okay, and now, so you can see that to keep these ratios at the same constant coefficient is very difficult. Okay. You cannot, so to give the force ratio and the length ratio and the velocity ratio is very difficult. But there is an easy way, which is the Buckingham's pi theorem. Okay, what is Buckingham's pi theorem? This theorem is that you are doing a dimensional analysis, and you find some non-dimensional variables, which we call them as pi. Okay, so for example, f by rho v squared by L squared, this can be one non-dimensional number. And the second one, non-dimensional means that they don't have any dimension. For example, rho v L by mu, it doesn't have any dimension. So the f rho v squared by L squared, it doesn't have any dimension. So So let me look at the rho VL by mu. So you can see that. So rho has a unit of kilograms per meter cube. In dimension, it is mass by L to the power of 3. Velocity has a unit of length by time dimension, and this one has a dimension of L. Divided by viscosity, which is the kilograms mass into length, and divided by time. Kilograms per length. Kilograms per meter second, length time. And if you do the calculation here, the time cancels out, this time cancels out, and this length, cancels out, this length cancels out, and this one too, and you will have the no dimension. Okay. So Buckingham's pi theorem generates non-dimensional numbers from a set of given equation. And if these non-dimensional numbers, which we call them as pi, okay, if it is the same between model and the prototype, then it is similar. Okay. If the pi's that is generated from given set of variables are the same between model and the prototype, then there is complete similarity between model and the prototype. So firstly, I will do an example for Buckingham's pi theorem, and then we will see how can we ensure the similarity between the model and the prototype. The example is, so there is a flow with density rho and viscosity mu, and it flows through the pipe of diameter d. Okay, there is a pipe diameter d and the fluid with a viscosity mu and the density rho. It flows through it, and the epsilon wall roughness, so that the wall of the pipe here, if you zoom in, you can see that. Okay, if you zoom in, you can see that it is not smooth, but it is rough. Okay, you can see the roughness elements here. And the flow with density rho and viscosity mu and the pipe diameter d and the roughness epsilon. And the velocity is the average velocity across the cross-section of the pipe. So you have the average velocity v, so across the cross-section of the pipe. And it remains constant during the flow by conservation of mass. Okay. So let me write the variables that is given. That is the rho, and you have the viscosity, you have the diameter, you have the epsilon, you have the velocity. Okay. And the shear stress is constant, and there is also shear stress by the fluid, because that by the pipe wall on the fluid, at the same time, Newton's third law says that fluid will apply shear stress on the wall. Okay, now the question says, using Buckingham's pi theorem. So first we will use it. How do we use it? We will see an example, and then we will see the importance of it. Develop non-dimensional relationship between shear stress and other parameters of the problem. The question says that the tower wall is function of the density, it is function of the viscosity, it is function of diameter, it is function of epsilon, it is function of the velocity. This is the relationship that is given. Inside the pipeline system, this shear stress is function of these 5 parameters. And it says that use Buckingham's pi theorem and to find relationship between these 5 variables. And for the pi theorem, we have the 5 steps that should be solved. Okay. Firstly, we should list all the variables. So for this problem, we have the tower wall and as well as these 5 variables, okay, which makes overall 6. Okay. And you should also be careful that if you have included the diameter, area should be included too. Okay. So the area should not be included, sorry, this one should not be included. If you have included diameter, they should not include the area, because that area is equal to pi d squared by 4. Okay. Therefore, no need to include both at the same time. Either you should include diameter or area. Anyway, for this problem, it is not an issue. So therefore, we have just written the number of the variables here, and there are 6 of them. This is the first step for the pi theorem. And the second step is that you are showing each variable with the primary dimensions. For example, tower wall, which is the shear stress, and shear stress is the force by area. And if you write in terms of the primary dimensions, it will be mass, length to the power of -1, and time to the power of -2. Or you can write the force as the mass into acceleration divided by the area. And this one is m, acceleration is L, time to the -2, and this one is L squared. And you can write this one as m, L -1, T -1. So T -2. Similarly, velocity L by T, epsilon L, which is meter, wall roughness. We have said it, this is the wall roughness, and there is some average length here, epsilon, which is average. Okay. And then the density, which is the mass by length to the power of -3, and the viscosity, mass, length to the -1, time to the -1, and diameter. Okay. And now we show that for the second step, how many primary dimensions do we have? For this problem, there are 3 of them: length, the mass, and the time. There are 3 primary dimensions for this problem. This is the second step. So from the first step, we have got that n is 6. From second step, we have got that j is 3. Okay, that the variables that only have lengths, they are called the geometric variables. They have also length and the time. These are called the kinematic variables. So it is related to velocity, kinematic variables. And this one is related to length, or it can be acceleration. And dynamic variables, they have included the mass. Okay, these are called the dynamic variables. For example, the force. Force is dynamic variable because it is mass into acceleration. Okay, now the step 3. This is a side note, which will be important for step 3. Step 3 is that we are determining the repeating parameters. And the most important part is that how do we select the repeating parameters? And the number of repeating parameters should be equal to j. We should have the number of repeating parameters. That one should be equal to j, and the j is 3 in this case, which is the number of primary dimensions. And what is the repeating parameter? Let me give you one example here. Say that you have found non-dimensional number, say pi 1. Okay, and this one was, for example, it is L by D. And you have got the second non-dimensional number, for example, and you've got this one as velocity by omega d. Okay, I've got the third non-dimensional number. So this too is okay. And you see that from first non-dimensional number and at the second non-dimensional number, diameter is repeated. It is at the first one, it is at the second one as well. This is the repeating parameter. It is repeated at each non-dimensional number. And that we have to first select which variables should be repeated. Which variables should be repeated, because that's an important step to generate the non-dimensional numbers. And there are some guidelines for choosing repeating variables. Firstly, we never pick the dependent variable. In our case, tau wall. Because if you remember, it was a function of the velocity, it was the function of the density, it was function of the length, epsilon, and the, was the, let's see that, viscosity and the velocity. This one was viscosity, and then rho v mu eta, and diameter. Okay, so we never select the tau wall because it is dependent variable. Second thing is that you cannot select the parameters that make a non-dimensionless group by themselves. For example, if you select for this one, if you select the epsilon and the d at the same time, this one has a dimension of meter, this one has a dimension of meter. And you can make epsilon by d, which is dimensionless. Okay, therefore you cannot select the two parameters that make a dimensionless group by themselves. And the third thing is that you cannot select dimensionless variables like the angle. And this is one of the most important steps. We select the common parameters. Common means that everybody knows it. For example, viscosity is not common, wall roughness is not common. Okay, these are not so common variables. Therefore, we don't select it. We select the common variables. And the simple parameters, of course, this one is also another important step. For example, energy is complex parameter, and therefore we don't select it. Or you can say that there is flow rate V dot versus velocity. Here it is better to select the velocity as the repeating parameter, because V dot is more complex with respect to velocity. Okay, there is no need to select it. Okay. And in the variables, we should have one kinematic variable. It means that L, one geometric variable. It means, velocity, one geometric variable, which is L, and one dynamic variable, which is mass. Okay. And if, of course, if the problem doesn't have the mass, then you can select these two here. Okay. Now let's select the repeating variables for our problem. So that tau volt, I've said it, it is function of the velocity, density, viscosity, epsilon, and the d. Firstly, we don't select, we have to select 3. I've said it, the number of repeating variables is 3, which is equal to primary dimensions. In our case, there are 3 primary dimensions, therefore 3 repeating variables. You cannot select tau volt, it is independent variable. You cannot select viscosity, it is not common. You cannot select epsilon, it is not common. Therefore, you have the velocity, you have the density, and you have the diameter. Okay, and the density is dynamic variable, diameter is kinematic variable, geometric variable, and the velocity is kinematic variable. You have each of them. Okay, now step 3 finished. Step 4, now we are generating pi values. Okay, that number of pi's, which are the non-dimensional numbers. Pi means that non-dimensional number. Okay, and the number of pi groups, which will be n minus j, which is equal to 3. So that number of pi's, which is n, total number of variables 6, minus the number of repeating parameters, which is 3, then you will have the 3 of them. You will have 3 non-dimensional variables, pi's. Let's generate them one by one. Okay, that first non-dimensional number, which is pi 1. What you are doing as a first for the generating the non-dimensional number, you write firstly you write the repeating parameters, which is the velocity, which is diameter, which is density. We did some power a1, b1, and the c1, and in front of them you write the parameter that is not repeated. Okay. For this question, rho v and the d is repeated, tau vol is not repeated, mu is not repeated, epsilon is not repeated. Therefore, you just write beginning from the first one, which is tau vol. Okay. And these should be dimensionless. Okay, and therefore you will have this one should be equal to m to the power of 0, L to the power of 0, and time to the power of 0, because it should be dimensionless. If that is the case, then you are just adding, for example, for the mass here. Mass has a power of 1, and this one has a power of c1, that's all. So therefore, for the mass unit, 1 plus c1 should be equal to 0. This one is for the mass. And next is L. So this one has a power of negative 1. Plus, this one has a power of a1. Plus, this one has a power of b1. Okay. And minus, this one has a power of negative 3 multiplied with c1. This one should be also 0. And for the time value here, we will have the time for the first one is negative 2, and for the second one is a1, and that's all. This one should also equal to 0. Okay. This is the first pi. If you solve this linear algebraic equation, you will get a1 is negative 2, b1 is 0, and the c1 is negative 1. Okay. And if you remember the equation, it was tau vol velocity to the power of a1, and diameter to the power of b1, rho to the power of c1. You just replace the values back here. A1 is negative 2, tau v, it means that velocity negative 2, diameter is 0, therefore it is 1, and the C1 is negative 1, rho to the power of negative 1. So the first non-dimensional number, pi 1, is this one, tau vol by rho v squared. Each non-dimensional number has some name assigned to them. This one is called Darcy friction factor. Okay. Anyway, this part is not so important. This is the first non-dimensional variable. Now comes the second non-dimensional variable. So in this case, instead of the tau vol, we will write the next non-repeated variable. Okay, which is the viscosity mu. And again, velocity to the power of A2, it should be very different from the first one, not A1, B1, C1. A2 and the B2 and the C2. You write the units of it. Mu is ml to the power of negative 1, time to the power of negative 1, and you will have the first term, you'll have the second term, and the third term. Okay. The powers of each term should be equal to 0. So for the viscosity, it will be that 1 plus C2 is 0. For the length, it will be negative 1 plus A2 plus B2 minus 3 to C2 is 0. For the time, you will have the negative A1 minus A2 is 0. You're just writing the powers. So this one should be equal to m to the power of 0, l to the power of 0, t to the power of 0. It should be non-dimensional. So the m is 1 here, and it is 1, therefore 1 plus C2. Similarly, l is negative 1 here, and A2 is here for this l is big. Okay, so you have written, you have solved it. A2 is negative 1, B2 negative 1, C2 negative 1. You just replace it back here, negative 1, negative 1, negative 1. So pi 2 is mu by rho Vd. This is the second non-dimensional number. Now comes the third non-dimensional number. Now you replace the epsilon. Next. Okay, next non-repeated variable. Okay, with the epsilon, you just write it again with a similar manner. You will get epsilon by d. This is pi 3. Okay, and with this one, we have finished the Buckingham's pi theorem, how it is done. And at the first equation that is given, tau vol was a function of that the rho, it was the function of v, velocity, so the viscosity actually, epsilon, and the diameter. This one was the initial. Okay, but after the dimensional analysis, what you have got is that tau vol divided by rho v squared. This one, what you have got from the first non-dimensional number. Okay, that one now is equal to function of different function of, so that will be function of the pi 1, which is that mu by rho Vd. Write it. It will be mu by rho Vd and epsilon by d. So with the dimensional analysis or Buckingham's pi theorem, what you have done is that you have decreased the number of variables 1, 2, 3, 4, 5, 6. Okay. It was initially a 6 variable. Okay. Now you have got the 3 variable. Okay. So you see, this one is dimensionless. This one is, you can say that these are just numbers. Okay. They don't have any dimension. Okay. And you have decreased the number of variables, which was 6 in the previous step. Now it is 3. This is the first important step that you have done. Okay. And the second important step that you have done is that by dimensional analysis, you can say that if you are doing an experiment, okay, so this one is the pipeline for water. Okay, and this pipeline, you are trying to find the shear stress, tau vol. Okay, but you are doing an experiment. This one is the real one. But you are doing an experiment not on water, but on air. Okay, and you are trying to find when air flows through the pipeline, what is the shear stress, tau vol. Okay, and to find that shear stress, okay, 1 minute. With the second, this one was the first step. And the second step is that, say that there is a real experiment, that water flows through the pipeline. Okay, this is the real experiment. And or it is not the water, say that it is some dangerous fluid. Say that it can be some toxic fluid, let's say. Okay. And then you are trying to find the shear stress that acts on this toxic fluid. Instead of doing the experiment with the real fluid, you can do the experiment even with air, or you can do the experiment even with water. It's not a problem. But what is the problem here? But you should be sure that these two experiments are similar. Okay. If these two experiments are similar, if the air experiment and the toxic fluid real one, if they are similar, then it means that whatever value that you get from your experiment here for air, you can know that with some coefficient, if you multiply it, you will get the same value for the toxic fluid. So how do we know that they are similar? If they are similar, we know that if pi1 for this one, which is the real one, is same as pi1 for the model. This is the first, and the pi2 for the real one should be same as pi2 for the model, or air. This one is air, and this one is toxic, and similarly here, this one is air, this one is toxic. If the pi's match, the pi values, if they are matching, then this experiment and that experiment doesn't have any difference. You will get the same values. Okay, you are trying to find what is the pump power here. If you do the experiment with the air, if you find the pump power with some coefficient, for example, 2 times, you will get the same pump power here. But coefficient is also determined by these variables here, non-dimensional variables. Okay, so another example is that, for example, water at 300 Kelvin flowing at an average speed of 3.909 meters per second through a pipe of inner diameter of 0.03 meters and average wall roughness of 0.03 millimeters. This one is the same as this one. They are the same stuff. Okay, they are the same stuff. How do we know that they are the same? So how do we know that these have the similar? How do we know that they are the same? Because we know that the pi's match. Okay, if the pi's match, then these two experiments are similar experiments. Okay? These two are similar. Okay? And for the first experiment, you can determine, for example, pump power. Okay, for the first experiment, and then since they are similar, you can find the pump power for this one. Find work dot pump from first experiment. Okay. You can find the pump power for the second one after you find for the first one. Okay. You don't calculate even for this one. If you know that one, you know that one, because they are the similar experiments. Okay. So similarity, we have said it. There are the ratios, the non-dimensional values here have the famous scientists. For example, rho VD by mu ratio is called the Reynolds number. This one is called Reynolds number, and the Reynolds number compares the inertial force, which is m into acceleration, to the viscous force, which is friction. Okay, or the V by square root of GL, it compares the inertial force to gravitational force. It's called Froude number, or Mach number, or so-called Mach number. So this one compares the velocity with the speed of sound. If you remember subsonic, supersonic, that is stuff that you have heard from the airplanes. Or the Stroll number, this one compares oscillation to the mean speed. Okay, and the lift and the drag coefficients, aerodynamics and hydrodynamics, important stuff. Okay, so this one is the non-dimensional numbers, and all of these non-dimensional numbers are generated by Buckingham's pi theorem. This one is all by Buckingham's pi theorem. And then you can have this non-dimensional number for your case. This can be your non-dimensional number. So there is one more example here. The example statement is as that, so that MIT, so these engineers of MIT, they have developed the tuna fish, named it robot tuna. Okay. This is robot mechanical, okay, and it has a length of 1 meter and has a maximum width of 2 meters per second. However, real tuna fish, okay, real, has a length of 2 meters and a speed up to 30 meters per second. How fast robot tuna should go for the same Reynolds number? Or you can say that in simple terms, how fast does the robot tuna, mechanical tuna, should go to be able to swim as the real tuna? Okay, you can say that to be able to swim as real tuna fish. How fast should it go to be able to swim as a real tuna fish? So to find it, you should know that this mechanical should be similar to real one. Okay, they should be similar. Okay, how do you know that they are similar? The pi's match. Okay, pi's match means that pi 1 is same as pi 2. Pi 1 for the mechanical tuna fish is same as the, sorry, pi 1. So this one is the mechanical and this one is the real. If they are matching with each other, and then you can find the speed that is required for the mechanical one to be able to swim. And for this problem, if you work out the Buckingham's pi theorem, you will get that this one should match by, you get this one by Buckingham's pi theorem. Okay. These two should match between the mechanical fish and the real fish. Okay. If you work it out, and you will get the velocities 20 meters per second. Okay, so there is one more example here. So this one is the for car example. So there is a car that the drag is to be experimented at 22.4 meters per second at 25 degrees Celsius. And 1/5 of the prototype is built, and the wind tunnel is temperature is kept at 5 degrees Celsius. So that this one is the model. Okay, so this one is the real, and this one is the real. Okay, this one is real, this one is the model car. So determine how fast should the wind tunnel run, and predict the aerodynamic drag on the prototype car if model car shows 94.3 newtons. Okay, this one is the model car. This is the wind tunnel. Okay, or that there is air flowing over that wind tunnel. And there is friction force acting on the car. Okay, and then the question is, how fast should the car in the wind tunnel should go to have the same conditions as the real one? So in other words, it asks the velocity of the real car, the model car, sorry. Okay, what will be the velocity of the model car to have the same conditions as the real one, and what will be the aerodynamic drag? It means that friction force. Okay. What should be the friction force on the prototype car if model car shows 94.3 newtons? Okay, so that to solve that question, so you should use the Buckingham's pi theorem. Okay, and the Buckingham's pi theorem says that if pi 1 of the model car is same as the pi 1 of the real car, for example, and the pi 2 of the model car is same as pi 2 of the real car, and therefore they are similar. Okay, and similarity means that you can find any property that you want. So firstly, if you work out the Buckingham pi theorem, you will get the rho v L by mu combination. Okay? And for similarity, this should match. This one is the pi prototype, and this one is the pi model. This should to match. Okay, and then from this calculation, you get that the model car should go at a speed of 98.8 meters per second. Okay, and the second non-dimensional number that you will get will be this one. Okay, this one is also by pi theorem. Okay. And from this calculation, you will get that the model force, if the model force is 94.3 newtons, in the real car it is 112.5 newtons. You can see the power of the dimensional analysis. You are just doing the experiment on the model one, and you are finding the values on the real one. Okay. That is the power of the dimensional analysis. And there is one more thing about the dimensional analysis, is that it is not always possible to match all of the pies at the same time. For example, let's give you one example. Say that we have a truck with a length of 15.9 meters and 26.8 meters per second. That is a truck. And we are trying to test the model of 0.99 meters. Okay, this is the model. For similarity, if they are similar, the Reynolds number or the pi that is equal to rho v d by mu. This should match with the prototype and the real one, okay, for similarity. And if you match them, you will see that the velocity for the model one, you need this amount of velocity for the model one to get the values, which is 429 meters per second. Okay, and this one is very large number, because if you calculate the Mach number, for the prototype it is very small Mach number, but for the model one it is very large Mach number. It means that here you can have the sonic boom or the shock wave, and due to shock waves you will have different flow pattern or different flow physics for the model one than the real one. Okay? Therefore, it is not always possible to completely match the similarity. Okay? Another example is that, for example, if you do the calculations for the boats and the ships, okay, for these two flows, for example, for boat or the ship, Reynolds and the Froude number must match. Okay, but if you do that, you will see that you will need very low viscous fluid, very low, okay, viscous fluid for the model, okay, very low viscosity for the model fluid, and in reality it doesn't exist. There is no such fluid that you can get with this viscosity value. Okay, this is again incomplete similarity. So it means that sometimes it is not possible to get the model of the real one. Okay, you have to do the experiment on the real one. The model is not possible. Okay, this shows that incomplete similarity says that model is not always possible. Or even it is possible, if you are trying to do the experiment, then you should neglect some values, some variables. Okay, so with this one, I have finished the lecture and I'm stopping the recording now. If you have